Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my pleasure to introduce today's speaker, Raman Zabi from Cornell University. Raman is the world's foremost expert on graph cut techniques applied to computer vision. Since 2001, he's also been has an appointment at the Radiology School of Cornell, which is located in Manhattan, which is where he spends most of his time these days. And he's going to tell us about some new ideas. He was telling me they're somewhat half-baked, so that should make them more exciting, on newer things to do with graph cuts.
Thanks, Rick. Yeah, so half-baked, flaky, take your pick. The title of my talk is Some New Directions in Energy Minimization with Graph Cuts, and I'll be talking about joint work with Jungwon Kim and Vladimir Kolmogorov. There's a theory that you never begin a talk with an apology, which I'm about to violate. But I do want to sort of point out that as a general rule, when you come and give a talk, in front of your friends, the idea is the typical thing you do is you say, look, I've solved a problem that, everyone knows about and people didn't know how to solve. That's what a lot of talks are like. That's not this talk. This talk is a little more like an attempt to get people interested in a particular problem. It's somewhere in between a technical problem and a way of thinking about a certain class of problems, which I think is actually quite interesting. And many of you in the audience have worked in sort of related areas. Some of you have even used graph cut algorithms on other problems. So what I'm going to try to convey to you is what I think of as being sort of an exciting new problem research direction. It borrows ideas from mutual information in EM. It doesn't actually use mutual information or EM per se, but it sort of borrows big ideas of their technical ideas. And a lot of the nice math that used to be, that applies in the world of graph cuts, no longer quite applies to these problems, but I still think they're actually quite interesting. Lest you think that this talk is completely half-baked, I am going to show you some preliminary results, and there are some things where we have some progress. But as I said, I think mostly what I want you to get away from, come away with from this talk is sort of more in the vein of here's an interesting problem definition, and here's a way that I kind of think about it, and maybe you have some ideas of following up on that. Okay, so the outline. I'm going to begin by sort of briefly trying to set the context for this work, and just spend a few moments going over the fact that you can actually solve a reasonable number of energy minimization problems in vision using graph cuts. So one way of motivating what I'm going to be talking about today is by trying to figure out how to solve a much broader class of problems. And I'm not going to give you a precise problem definition yet, but for the moment, just think about the kinds of issues that show up in like multimodal correspondence, maybe when one of the images, one of the two cameras is much brighter than the other, for instance. Layered motion segmentation, a topic on which there's been an enormous amount of work by people in this room. Texture segmentation, problems like that. They're interesting problems. One question is, could you actually use these kinds of combinatorial optimization techniques like graph cuts to solve those problems? Some interesting technical challenges, I think. And I'm going to show you, for most of my talk, sort of two initial results. A result showing how to use how to compute visual correspondence using ideas borrowed from mutual information, together with energy minimization with graph cuts. And then, in the least baked portion of this talk, an idea that I'm really excited about, but it's very preliminary, called spatially coherent clustering. Let me just very briefly review what you can sort of already do with graph cuts, and since this was sort of partly in my talk at Washington and it's reasonably commonly known, I'll try to fly through this. So you've got a set of pixels in a neighborhood system and a set of labels. The labels you can think of as being colors. There's an assignment cost that tells you how much each pixel likes each particular color. That's actually going to be very important for this talk, so we'll call that D. And then there's a separation cost for assigning pairs of labels to neighboring nodes, which we'll write as B. And what you want to do is define a good labeling. You can, of course, naturally set this up as an energy minimization problem. And in fact, we'll see a little bit later on in this talk that one of there are many advantages to formulating problems in terms of energy minimization, as long as you can then solve the resulting energy minimization problem. Because you essentially just write down, what properties you want your solution to have, and you want the assignment cost to be good. You want every pixel to be fairly happy with what it's being labeled, and furthermore, you want the separation cost not to be too expensive. You want, if it's very expensive to have a particular pair of colors next to each other, you don't want them to be next to each other. And then graph cuts sort of allow you to solve this problem, and I'm going to have to just briefly review this. So for the stereo problem, of course, the labels will be shifts. Notice that at the correct disparity D, the intensity at I1 and I2, sort of corresponding pixels, should be roughly similar. And that, of course, leads to a natural notion of the assignment cost. People actually use more complicated assignment costs than this. Honestly, you can use this assignment cost and things work pretty well. But it's something like this. It's something that's, and this makes it expensive to have a disparity that maps you to a pixel with very different intensities. And then, of course, you want neighboring pixels to have sort of similar depths. Lots of different ways of doing that, and of course, you want that not to be enforced to the border of objects. Okay, and then you can you can solve this energy minimization problem using graph cuts. Technically, it's based on the minimum cost ST cut on a graph. An amusing piece of trivia, I tend to call that, I tend to use the phrase graph cuts for that informally. I think I actually stole that from Rick. Because it's not a phrase that's used in the algorithms community, but it's a good, it's a catchy word. It computes a strong local minimum in a certain sense. It gives you a strong local minimum even if you allow very large moves. And the primary example of this is the expansion move algorithm, which I'll talk about. For the purposes of this talk, what's most interesting about the expansion move algorithm is that not only does it give you pretty strong results, it really doesn't care where you initialize it. It doesn't care in terms of its running time, and it doesn't care in terms of the result. I'll show you in most of this talk algorithms that no longer have that property. It's a desirable property to have. Okay, just to briefly review the expansion move algorithm, you start off with an input labeling F. Here's a red expansion move from F. All I've done is I've increased the set of pixels that have the color red. The algorithm works as follows. You find the red expansion move that most reduces the energy. Then you go there. And you find the best blue expansion move, et cetera, et cetera. Keep on doing this. And you're done when there's no expansion move that decreases the energy for any label. And it rapidly computes a strong local minimum. It has a number of very nice theoretical properties, none of which will apply to anything that I'm going to talk about later on in this talk. So this is kind of the wistful look at the clean world that I used to live in. And then, of course, there's some nice results. The accuracy is about roughly 3 times as good as sort of what was commonly used when the work on graph cuts began. So here's one example, and here's another example of what we can do. Okay, so much for the intro. Where do we go from here? Well, so this is the energy function that we sort of know how to minimize pretty well. And, what else can we do? There's some very nice results from Vladimir's PhD thesis that essentially say you can use graph cuts on this for an arbitrary choice of D and an important class of V. Okay, and so the natural thing to do is to work on sort of expanding the set of V's, because after all, it's sort of limited. That's a natural thing to do. I'm going to try to persuade you that it's the wrong thing to do. I think that actually looking at D is much more interesting, and I hope to sort of persuade you of that in this talk. There's sort of several reasons for that, but the primary reason is, well, you'll see in the rest of this talk, there's some very cool things you can do with strange Ds. Remember, D is sort of how happy the pixel P is to be given a particular label. But another thing that's worth mentioning is that even though the important class, the class of V's that graph cuts can handle is limited, in practice, it covers some pretty important cases, some cases that show up a lot. And even though it kind of likes fronto-parallel surfaces that are oriented sort of like this with respect to the camera, with some cleverness, you can make it handle sloped surfaces and curved surfaces. And there's work by Carlo Tomasi and his students that does that, and it actually is currently at the top of Rick and Daniel's benchmarks. Those sorts of methods tend to perform very well. So I want to argue for more general assignment costs, more general choices of D. Well, that's kind of weird. Yes?
This work by Tomasi involves having discrete labels over surfaces which then have analog parameters.
That's right. But he essentially still used the Potts model choice of V. Right. So it's kind of remarkable that the Potts model, even though it seems to like fronto-parallel surfaces, what it really likes is consistent labelings. And if you sort of tweak your labeling set to include like slope surfaces, then you can do it. And there's an early paper with Stan Birchfield in ICCV, and a more recent paper in CVPR03 with Mike Lynn, I think was the PhD student's name. Okay, so what could be more general than completely general? Well, let's think a bit about assignment costs and labels. And the thing I want you to notice is that the assignment costs and the label set are specified in advance. Okay, they're part of the input to the problem. So if you sort of try to use graph cuts for repeating visual correspondence, the problem definition that I showed you a few slides ago is here's your D and here's your V, right? And the choice of D, how happy is the pixel P to have the disparity D? Well, this is the cost of assigning P the disparity D. Okay, it's part of your input. Now, let's look at a little motivating example here. It's worth realizing that this choice of D, particularly for like a stereo problem, essentially makes the constant brightness assumption. It says that, you know, look, at the right disparity, I1 of P is going to be pretty similar to I2 of P plus D. Okay, but there are a lot of interesting situations where this assumption is violated, and by looking at those, I hope to sort of show you why more general Ds are interesting. Okay, and here I'm going to talk for a little while about work that John and Vladimir and I published in ICCP. Okay, so to talk briefly about this multimodal correspondence problem, it's just sort of a variant of visual correspondence. Let's imagine that our two cameras are actually pretty different. Maybe one of them is a lot darker than the other. They have different internal parameters. Maybe one of them is an IR camera, or one is another one. If you're happen to be working in a medical school, perhaps one of them is CT and one of them is MR. But I'm going to assume, just to simplify things a little bit, that there's some consistent mapping of intensities between them, which I'll write as mu. And at the right disparity, I1 of P is mu of the corresponding pixel, of the pixel that corresponds to P. And to give you sort of a little example, let's suppose that mu just takes intensity and doubles it. So now I've got one camera which is half as bright as the other. Now, what happens if you take that pair of images and run them on your favorite stereo algorithm? Well, I don't know what your favorite stereo algorithm is. I happen to know what mine is. I'll bet you can guess. It gives you this really cool-looking, but utterly useless answer. Why exactly it sort of decides to divide the face in two, who knows? Not particularly useful, but cool. And what I'm going to show you in this talk is a result which is not necessarily very useful, but sort of cool, which is that you can do weird distortions to your images and still get actually very high-quality answers. That's going to be sort of the punchline for this part of the talk. Okay, so, but why not just do it? You know, you have, I sort of showed you what the transformation of what happens when you have a transformation of intensities. Some of us have a lot of experience applying graph cuts to various problems. Why not just give it a shot? You can't. And the reason is that at the beginning of the day, when you're sort of given the problem, here's my pair of images, you have no idea what the assignment cost is. Okay? In the old world, where you're doing visual correspondence, you know how happy this pixel is to be assigned this disparity, how happy it is to be mapped to this other pixel. You just say, look, how close are their disparities? If they're similar, that's good. If they're not similar, that's bad. Okay? Now think about this. In one of these situations, you know, it can be perfectly fine to be mapped to a disparity that's very different than yours, depending upon what mu is. You can't tell how much P likes D. The right data cost is something like this, right? It's the difference between the intensity in I1 and the intensity in I2, where it's been sort of distorted by this transformation mu. Well, it depends upon mu, but guess what? You don't know mu. Mu is a part of your input. You just get these images. Now, you could compute mu from the right F. Okay? If I had the right F, sort of what pixels correspond to each other, from that I can essentially, by fitting, just compute what the intensity transformation is. Does that make sense? So this, of course, suggests an EM style approach. I'm not going to say, I should say very clearly, I'm not doing EM. But there's sort of a style, there's an EM style of approach here that springs to mind, which is, look, you're going to alternate between estimating the assignment cost, D, and estimating the labeling, F. Okay, so you start off with some guess from you. That gives you using that guess, that gives you the assignment costs by this formula. Using that set of assignment costs, you get a labeling. That labeling, in turn, gives you another guess from you, and you just go round and round. Okay? I think fairly intuitive notion. So what is the assignment cost? Well, we're going to compute it from a particular labeling F. It's not part of the input. And in order to talk about it, I need to introduce a concept called the joint histogram of intensities, which I actually think, in my current view of how to teach stereo, this is actually a very useful concept, even though it doesn't really, it wasn't sort of designed in the context of stereo, but I think it's a nice notion. Okay, so what's the joint histogram of intensities? Well, it's relative to a labeling F. It's a two-dimensional histogram. Histograms, of course, are counts. The x and y axes of it are intensities. The pixel P is in the bucket of its intensity in the left image and the intensity of the corresponding pixel under F in the right image. So to say that in words, that's what the bucket coordinates are. And I'll show you a nice picture of this in just a moment. Critical thing to remember is this depends upon the labeling F. Okay? So, let me show you an example. So we have our two images, and let's pretend at the moment we start off with a really great estimate for F. So we've got this pixel here in the left image, and according to the wonderful disparity map F that we have here, it's got this disparity, which means that it maps to this purple pixel over here. Now, the green and the purple pixel have two intensities. And the joint intensity histogram maps this pair of intensities into a bucket. Okay, so this is really what you end up with. All right, and now I can fill in this bucket with a count of how many pixels has, say, that pair of intensities. All right, does that make sense? And now you can do this for the entire image, right? And this is what it looks like. I'm going to show, when I show you joint intensity histograms, I'm going to display zeros in red, just because otherwise it's kind of hard to see them. And so what you're seeing here is that the left image on the whole is basically roughly twice as bright as the right image. In fact, these little sort of variations from that line are themselves kind of interesting. They're specularities or whatever. They're places where the model that says that mu is that we're sort of multiplying the intensities by 2 isn't really quite accurate. Okay, so that's the joint intensity histogram. Does that make sense? All right.
Do occlusions also show up?
Yeah, occlusions do not show up in this talk. There are places where there are other places where what about occlusions is a good question, and I'd like to preempt them all. Yeah, occlusions. No, actually, Steve, I'm sorry, I misunderstood your question. Yeah, occlusions are and in fact, as I said, I actually think that this tool is a really good way to teach stereo because, for example, what's the camera noise? It's the width of that. Right, it's more or less the bandwidth matrix. Question.
There's also maybe a mixed pixel issue.
Yes.
Which if you
there are mixed
based on
mixed pixel issues, which the answer is the same as the answer that I gave about occlusions. Yeah, it's it's definitely true, and it's in the list of things that I'm not going to try to handle at this point. Yep. We actually have some ideas about how to handle those issues, but they're not really in the sort of center or mass of this talk. Assuming this talk actually has a center. Okay. So the natural way to solve this problem is with an EM-style approach. Now, when F is correct, I happened to show you in the previous one the correct choice of F, The joint histogram is going to be highly concentrated. Most of the entries are going to be empty. If you think of, a row in the joint histogram, row in the histogram tells you where left intensity 100 mapped to, and it's going to almost always go to, say, 50, whereas at a bad disparity map F, the opposite is true. So if F is good, the joint histogram is highly concentrated. If F is bad, the joint histogram is highly sort of non-concentrated, sort of spread out. Okay? Yeah, Steve?
So it seems like this assumes that mu is spatially invariant.
We don't actually, we will relax that assumption later on. Yeah. In an ideal world, if you think of this talk as being how to do better stereo, which really isn't quite its focus, but if you think of this talk as how to do better stereo, what you really want is mu to capture things like, texturing differences, highlights, all that kind of stuff. We actually played a little bit with specularities, with results that we're not showing here.
Even of like vignetting,
Yeah, that's right.
Images.
Yeah, that's right. So we'll be able to handle them. But I was skating over them in the intro. But as I said, I like this joint histogram way of thinking about the stereo problem. So what are we going to do? Well, it's actually really simple. For a given f, okay, so when we sort of have a particular labeling of the pixels, we can sort of build an assignment cost that tends to make the joint histogram more concentrated. Okay, and that's the trick that we're actually going to play. And then using this assignment cost, we can have this sort of iterative EM-style algorithm where we find f given the assignment cost, and we find the assignment cost given f. Okay, so really, what I told you on this slide that's new is that there's some measure hiding here of joint histogram, of the concentration of a joint histogram, and that our assignment costs are going to sort of try to make the joint histogram more concentrated. Okay?
Why is this EM-style algorithm as opposed to EM algorithm?
Yeah, good question. I tend to think that if you actually want to call it, hey Paul, if you want to really call it EM, especially in front of people who really understand EM, you need to sort of set it up as a maximum likelihood estimation problem with hidden variables. Okay, which I haven't done. It's probably doable. So it's an attempt. It's the same reason why I'm not quite saying it really uses, if I abstract it carefully, where it uses ideas from mutual information and expectation-maximization. It's probably something, so I'll show you the problem generalization in a few moments, and maybe there's actually a straightforward way of turning that into a hidden variable problem. Perhaps there is. But I'm trying to either be modest or avoid getting in trouble, perhaps both. Okay, so how do you compute the assignment cost? Well, let's go back to our little image. The assignment cost, you want to know how happy this pixel is going to different places. So here's one place it could go. It could go to the purple pixel, that happens to be where it ought to go, or it could go someplace random, like, say, on the lamp. Okay. Now, if it goes to the purple pixel, then there's an entry in the joint histogram. If it goes to the blue pixel, there's some different entry in the joint histogram. Okay? So now, what we want is to figure out what the cost is of this green pixel deciding to go here versus here. Okay? And the cost is essentially going to say, look, it's expensive to go to a place which tends to make the joint histogram not concentrated, and it's cheap to go to a place that makes the joint histogram more concentrated. Very, very simple, intuitive notion, I think. So here's the joint histogram again. And now, of course, you can say, hey, that's a good place to go. Why? Well, not because I'm cheating and I know it goes there, because looking down here at the joint histogram, that's a good place to go because it's popular. It's got a lot of stuff in it. Okay. If you think about, when you change the disparity, you're sort of moving pixels around in the joint histogram, and you want them to go to places that are popular. Okay. Have a lot of other pixels in them. That's a bad place to go. Okay. Now, of course, there's a little problem hiding here, which is that while each pixel is sort of trying to decide, well, I want to go here because it's popular, and I don't want to go there because it's not popular, you want to go here because it's popular. Meanwhile, all the guys who are already there are making their own decisions. right? So there's a little complexity involved here. But so this is sort of the basic idea. Okay, is that clear? All right. So let me now try to formalize this. And as I said, perhaps there actually is a nice EM way of thinking about this this problem. So here's the problem we know how to solve. Okay, with graph cuts. This for any D and for lots of choices of V, lots of interesting choices of V. Now the problem is that in the problems I'm looking at, D actually depends upon the labeling. Okay, it's not part of the input. At the beginning, you just have no idea what the assignment costs are. So what you do instead is an iterative approach where on the nth iteration around, you have some sort of guess at the nth step as to what D is. You solve this problem that we all know how to solve for that particular choice of D. From that, you compute Dn plus 1, and then you plug it back in, that gives you Fn plus 1. Okay? And that's how this whole scheme works. Any questions? Yes? Yeah, there's actually some tricks you can do to make it somewhat to make it somewhat faster. But yeah, the computing histogram on these things, I mean, it's not hugely expensive by the standards of the stuff that you do with these algorithms anyway.
And also, isn't it, in your experience, do you overtrain? Do you have enough information to train it? Because it's a very large histogram that you're trying to train.
Yeah, it works. Maybe that's a good way of describing it. It does a spectacular, one way of thinking about it is, this algorithm does a spectacular job of doing a problem of no clear interest. Okay, you really can't, I'll show you just a couple of examples. You really can take your favorite stereo pair, apply some totally wacko transformation to it, not even a spatially uniform one. You can take the bottom half and double it and the top half and multiply by quarter, and you will get high quality answers. They're not quite as good as the best answers for if you didn't do that warping. So the histogram is dense enough, but it's related to another interesting question we'll come to in a moment. Rick? Excellent question. Yeah. So there's a general fact here that most of the nice mathematical properties of graph cuts are no longer apply in this case, and it is conceivable on iterations for the energy to go up. It doesn't happen in practice, and you do monitor it. Okay. So that's the basic notion. Let me tell you a couple of properties of this. Here's a totally wild property of this algorithm. An interesting accidental property of this algorithm that has nothing to do with graph cuts. It's actually just a way of computing assignment costs, okay, iteratively. So you could actually use this with correlation if you wanted to. I haven't done this experiment. It would be kind of interesting. You could certainly use it with belief propagation, which just tells you how to compute the data costs. Okay, and if you think of correlation, well, correlation basically says, find the disparity that sort of minimizes the data costs and, sort of locally at each pixel, some of the data costs in some window. It can handle, as Steve asked about, spatially varying choices of mu. One obvious question about this, I think, maybe it's implicit in some of the earlier questions, is why on earth would this method work at all? And if you think about it, given the way I've sort of set up the problem, for the method to converge, you have sort of two requirements. You need a decent guess as to the initial data costs, and you need it to be the case that they don't change a huge amount between iterations. Okay, since if they're wildly fluctuating, you're not going to get convergent, because essentially you're assuming that Dn plus 1 and Dn are somewhat similar to each other. Now, that's not the same as assuming that the intensity map, that the labeling that the labeling of pixels changes. It doesn't change much from one to another. But this latter property is sort of particularly worrisome because in a certain sense, that property actually says you're better off with a crummy optimization algorithm. Okay? Because after all, a good optimization algorithm will change labeling a lot. But you'll see it actually works quite well, and I'll give you the demonstrations in a moment. This may be, a demonstration of being really lucky, but these two not-so-obvious properties are easily true for the visual correspondence problem. Anyone have any guesses why? Why are these things actually true for visual correspondence? I'll show you in just a moment, but it has to do with some. It's not true of arbitrary problems, but it's true for visual correspondence. Yeah.
One of them.
Yeah.
Well, no, I've done all this before.
I know. I figured you probably do, Paul. Yeah. Yeah. But actually, if you don't know, it's not obvious, right? It's a strange set of properties, and it just happens that visual correspondence happens. It's got to do with the fact that images are smooth and disparities are small. In fact, to do it really precisely, it's a relationship between the scale of variation in the images and the disparities you allow. It's also, thanks Paul for the intro, related to useful information, which we'll talk about in just a moment, with the right formula for D. I didn't actually tell you how to compute D. I just sort of said, well, you want it to be expensive to go to empty areas of the histogram and cheap to go to popular area of the histogram. But it turns out that with the right formula for D, it actually has a nice relationship to useful information. So before I go into that, though, I'm going to just show you it in action. Okay, so here's our pair of input images. Here's our disparity map, a very good initial guess. You might sort of think that the joint intensity histogram you compute from this is going to be garbage. But you would be wrong. It actually has a lot of structure. So why does it look, and you can see, by the way, that the right answer is going to end up being just a line like that. Okay, so why does that look so good? Well, it's basically what Paul was alluding to. The thing is that even if you pick a totally random disparity, you're going to tend to map something from the left image into something that's about half its intensity in the right image. Yes. Yes. Fair enough. Yeah. As I said, one could. I'm sure there's actually a beautiful theorem. You probably know its name, right? I'm sure there's a beautiful result that sort of says, if the disparity, versus the scale of variation of the image, blah blah blah. I don't know what that result is. Yeah.
What does this look like if your image gets below 0?
Yeah. You get the same thing. This is actually an attempt to show you what happens in the worst case. We started off with garbage. That's cool. What happens? So basically, as long as I said, as long as whatever that relationship is holds between the disparities and
garbage in this case being a number between 0 and 16 pixels.
Exactly.
To the right.
That's right. So although I suspect that. If I were, the problem is that the right theorem here is sort of one of these. It's the kind of theorem that you study in image processing classes involving like Gauss-Markov models of how intensity variation. Yeah, blah blah blah. I don't know that stuff, so I don't know what that theorem is. Maybe I should. Yeah, exactly. But you guys are right. So you have the right intuition. But watch this. Okay, Shazam. Random garbage from this, which is not quite so random. You compute the disparity cost. From that, you compute pretty good guess. And now, things are really good. Okay. So this is not going to win first place on the Sharstein-Zalewski benchmarks, but it's a lot better than anything that was out there. I think except for the top class of algorithms, it's actually pretty good, and it can handle these bizarre distortions. So let's do something else. Gen 1 sort of came up with this bizarre function here, which I'll show you in just a moment, and I think it's actually a spatially varying bizarre function of the intensities. And here's our random garbage. And, well, looks like there's structure here. The function here does that. Attempts by me to get Gen 1 to explain what that function, why on earth that function makes any sense, have failed. But it's some weird distortion. Get something pretty good. Go around one more time. Get something pretty good. Okay, so maybe we're living right. Somehow images kind of have this property. Now, if you think about this, it ought to not work all the time. You ought to be able to construct cases where it fails. Certainly you could construct synthetic images where it fails, like random dot stereograms where it fails. But even in terms of real images, you ought to get in trouble if the disparity range is large and the images are highly textured. Okay. The only thing that happens experimentally is that if the disparity range is that when you run this on more highly textured images, it takes a little bit longer to converge. Okay, so I've shown you sort of what happens like one or two iterations. Most of the right thing happens, you know, the first time that you run graph cuts with basically the first time you run graph cuts. But if you run it on things like the SRI tree images, which actually have about as much texture as any stereo pair out there, what happens is it converges a little more slowly. So it takes about 4 or 5 iterations to get to the right place. But I haven't seen any examples where it doesn't actually work. Okay, let me show you just some synthetic distortions. You can do all kinds of bizarre things to your image. So that's what it does when you don't do anything to your image. You know, good, but not quite at the top of the list. There's the tree image. Here's what happens if you divide by 2. And here's what happens, by the way, when you do the same distortion to the tree image. Here's this other bizarre thing, and it's kind of striking that there's actually, you know, here I've sort of done 2 different transformations below and above this line, but you can't actually see that line in the data. So, okay, so much for everything except for the mutual information relationship of this part of this talk. Does that make sense? Any questions? Okay, so let me now...
One thing about the spatial
Yes.
vary.
Mm-hmm.
So there's the same function kind of going on, at least in large sections of the image, as opposed
Yes.
to sort of thinking more like a vignetting kind
Yeah.
of thing, where the function is varying
Yeah.
in a smooth way,
Yep.
not, you know, discrete chunks.
Yep.
But still expected to
Yeah, so I'll tell you the way that I think about it. It would actually be very good to try those experiments. You know, so it sounds like you guys actually may have cases. I think of this as a cool toy to solve a useless problem, basically. It sounds like you may actually have some examples where it would be useful, and that'd be great. We haven't played with those. I think that the way you want to think about it is as long as the intensity, as long as the joint histogram ends up being concentrated, you're in good shape. Okay, so... And I think, yeah, I think even with those, it would be highly likely to end up being concentrated. Because bear in mind, the true solution isn't incredibly concentrated either. You do, I mean, I showed you these examples with the ground truth on the on that Tsukuba image data set. But that'd be very interesting to try. It's not hard to do this, right? There's some math in the paper. Honestly, I think if you just hacked up your favorite D function, you know, sort of does the right thing in terms of the joint histogram, you'd probably get good results, I'm guessing. So.
Completely randomly, as long as it's a small number of deformation functions, intensity deformation functions.
Well,
because you're completely, when you're computing a histogram, you're not looking at the spatial.
That's right. That's right. You aren't using well, you need, yeah, you need you need either a small set of them, or you could have a larger set of them, as long as they kind of, again, I think the way you want to think about it is, if you had the right answer, what would the joint histogram look like? Right, and if you had a spatially varying thing that jumped all over, that was really wildly varying.
No, it varies continuously. So, you know, you've got that in the original one, you have this chart, you know, 2 times.
Yeah.
So let's say in the center, it's 1 times. By the time you get to a little bit out, it's a little less, a little less, a little less. By the time you get out here, 5 times. So now you've got this line that's kind of, you know, spread that line out over the
Yeah. It would such things out.
Varying information, then you might have a problem. If it's but in case of the last image, for instance, where it's like 2 things, if it's just completely scattered across, if every other pixel has half and every other has
right. But also, Michael, so your function is changing, but also, Michael, while your function is changing within a particular value of that function, you're not going to see all possible intensities. So, my intuition is that it would probably work, but it's definitely something worth trying. Be interesting to know. Okay. So, Paul, you can close your eyes here, and I will attempt to explain the relationship between this and mutual information. Okay, so mutual information, as some of you in the audience perhaps know, is a very powerful method for multimodal registration. Okay, so think of registration as, you know, trying to line up the images, and the registration problem is to find the affine transformation, or if you will, the warping of I1 that makes it most similar to I2. Now, a warping of the images implies a joint histogram. Okay, if I sort of warp image number 1 so that I line it up over image number 2, then I've essentially implied a correspondence between those pixels, and from that correspondence, you have a joint histogram. In fact, you can think of, you know, carrying coals in the vein of carrying coals to Newcastle, because there are several papers by authors in this room that sort of take this view. You can actually think of a disparity map as just a very complicated warping. Okay, it's got a whole lot of parameters. MI measures, I should say this very carefully. For the purposes of this talk, I will claim what mutual information does is it measures the concentration of a joint histogram. I'm actually sliding over a number of issues. Notably, the fact that what I'm talking about isn't really quite mutual information; it's really joint entropy. But they're the same under certain circumstances. As long as you don't worry about things like occlusions, they're pretty much the same. So mutual information is this way of sort of telling you how good a transformation is, and then you search using gradient descent. And these methods are very successful in practice. It's very widely used. There are hundreds of papers on this. This leads to the obvious question: why not just use mutual information for visual correspondence? It's a nice way of handling all kinds of strange, intensive deformations. And the reason that no one did it before is that it's just not really possible. There isn't really an obvious way to apply it. The methods that people use for maximizing mutual information do gradient descent. In an affine transformation, you've got fixed parameters. If you think of a disparity map as a warping, it has 100,000 parameters. Right? You just can't do gradient descent in that kind of space. It's just not going to work. So what you want to do, and this is kind of one way of looking at what this paper sort of showed how to do, is to turn mutual information into an assignment cost. Let me kind of try to make this a little bit more precise. You would like it to be the case that in the event that your separation function v did nothing, okay, suppose that v always says no matter, any two neighbors are always fine, doesn't matter, same difference, no cost, a fixed uniform cost, then what you'd like to do is to have an energy function where the energy of a labeling is the mutual information of that labeling sort of used as a warping applied to that pair of images. Okay. And there, unfortunately, you run into a problem, which is that mutual information is actually not in the right form. Okay. A measure of the concentration of the joint histogram is not a sum over pixels. Okay, that's actually sort of technically the heart of the problem. Okay, every pixel doesn't independently make the joint histogram concentrated. In fact, if you go back to the Bayesian MRF way of looking at these energy functions, right, there's a point when you're deriving the standard data term, you have to assume that all pixels contribute independently, right? And that sort of notion of the pixels contributing independently doesn't actually work in terms of mutual information. It's not in the right form. So then what is the relationship between this work and mutual information? Well, it turns out that there actually is kind of a nice relationship, without which this paper probably would never have made it into ICZV. Let's imagine that we have two labelings of pixels, two disparity maps, F and G, and let's pretend that their joint histograms are somewhat similar. Now, bear in mind, I am not assuming that these are similar, that the labelings themselves are similar. I'm merely assuming that the joint histograms are somewhat similar. Okay. Let's take the Taylor expansion for mutual information with labeling F, and let's take the Taylor expansion centered at G. And if you take the first term of it, that's actually a sum over pixels. So if you sort of put this all together, if you choose D appropriately, and actually it turns out that the choice of D that's correct is kind of natural. It's sort of a nice one. You can actually approximate MI. Okay, so you can sort of view this whole thing as sort of giving you a data cost which approximates the mutual information data cost. Paul, did I make any grievous errors in this?
Yeah, it's got a really simple form. It's just
yeah.
Pairwise squared difference between all pairs.
Yeah, exactly. Yep. I was trying to avoid equations, but yeah, that's right. Yeah. It's a very natural thing, and honestly, if you were to ignore mutual information and just sort of say what's a reasonable data cost, right, that sort of tends to make histograms concentrated, you'd say something sort of like that. I mean, for example, you obviously need to kind of smooth out the histogram, right? Because if you have, I'm going to draw here. If you have, a couple of buckets in the histogram, there's the histogram. Here's some things. If this guy has, 100 pixels in it, this guy has, 75 pixels in it, this guy just happens to have 0 in it, well, that's probably a good place to be, So you want to do some kind of smoothing, and that turns out to be related to parse and estimation, et cetera, et cetera. So I think it's a very nice relationship. Okay. There, by the way, there are one or two previous attempts to apply mutual information to visual correspondence, which just really don't work at all. It's essentially because they don't set it up as an energy minimization problem. Okay. Yeah, so as I said, the choice of D is fairly natural. Okay, so let me now attempt to summarize part one of this talk. So the multimodal correspondence problem can be solved using energy minimization. It has this kind of bizarre recursive structure to it, where the assignment costs depend upon the labeling, and where you essentially have to sort of iterate between them. Under the right circumstances, you can prove something about its approximating mutual information. It's an EM style use of graph cuts. Perhaps there's actually something rigorous you can say about the use of EM here. Probably nothing rigorous that I would say that I'm familiar with. The experimental results are actually pretty promising for, given the fact that we didn't really have any real test cases, but it sounds like there may actually be some real applications. That would, of course, be really nice. I mean, yeah, question?
So the way you make it EM, you are treating the probability distribution over pixels as a parameter in the model, where basically in the second image, I2 of P plus D is probability distribution indexed by the color in the first image. Yeah. And then basically we'll end up having to learn full distributions, full histograms per color in the previous image, which is exactly what you're doing, because you learn to 2D join histogram.
Yeah, now the thing is that what I want you guys to sort of take away from this talk primarily is a little bit more general than this particular example. It's got to do with these sort of data terms that are defined in terms of labelings. So I think that the right formulation of the problem, and I suspect that something that you're right, that there is some generalization like that, would be one that doesn't really talk about joint histograms per se or color, but sort of talks about there sort of being a hidden variables of data cost. It's not obvious to me, but I'm not an EM guy, so it would be
separate the observation model from the index model.
Yeah, it would be very interesting for someone to do that. I'd love someone to do that. I'd love to do the paper. I'm obviously not the person who's going to do that. Okay, so then the last thing I want to mention is what actually can you prove about this? Well, just about nothing. Graph cuts have all these nice mathematical guarantees, expansion moves, approximation algorithms, etc. Well, you can't prove much about what this algorithm actually does, but let's kind of work. Okay. So let me now move to the much less vague, but I think, at least to me, more exciting portion of this talk, which is about a technique that I call spatially coherent clustering. And this will be in CVPR. So there's a common technique in computer vision, shows up for many applications, called feature space analysis. And it's used for segmentation, it's used for layering, it's used for texture. Let me briefly describe for you how it works. At a particular pixel P, we'll compute a feature vector XP, which is just some set of numbers that characterize this pixel. And the obvious trivial example is just intensity, or maybe it's the three intensity values. Okay. This by doing this operation at every pixel, we can map the entire image into the feature space, which I'll call capital X. Then what you do is you cluster this feature space into, say, k clusters, and throughout this talk, I'm going to assume that the number of clusters is fixed. We have some work that tries to relax that assumption, but it makes life a lot simpler in terms of the notation. So you take your image, you divide it into clusters, you map back it, and you take your image, you map it into feature space, cluster your feature space, map back into image space. That's your segmentation. Okay. This is a very common, very powerful technique used all over the place. Question: what about spatial coherence? What in this technique actually causes you to get spatial coherence? And the answer, of course, is nothing. Yes. We'll show you some really spectacular examples of failure of that, but that is in fact what people do. Yep. You're either, I think you're exactly 1/2 slide ahead of me. Many well-known bad solutions. The standard thing that people do, by the way, is they just sort of do this and they say, well, it's about right, and then we kind of run some morphological junk to clean up afterwards. It'd be nice if your algorithm didn't introduce bad behavior. A popular choice, Michael, you were exactly 3 small bullets ahead of me, is using position as a feature. Okay, so along with, intensity or whatever, you also compute the XY position. There's actually a kind of nice quote about positional features that sort of makes two nice points about them. One is that it doesn't really work, okay? And the other is that even though it doesn't really work, it's better than just ignoring spatial information completely. That's actually from Jitendra's paper, the Blog World paper from 2002. Okay, so let me show you a simple example. Let me sort of tell you this is probably pretty obvious, but at the risk of belaboring it, let me sort of sketch for you what you would kind of like to see happen here. So here's an image. Generally what happens, let's pretend that our features are just intensities, is what you're hoping to see is when you map this into intensity space, compute the intensity of every pixel, make a histogram, here's the count, here's the intensity. Take this, cluster this, map that back to the image, and that bump will be on the inside, and that bump will be on the outside. All right, that's what you're hoping to see. Care to guess what the histogram looks like for that? How about that? All right, they just happen to be the case that these Gaussians are not real well separated.
How come we can see the difference?
Good question. I guess we're smarter than computers. Well, they are separate. They're not identical, but the overall histogram. That's right. So this is what happens. This is the output that you get from using clustering in feature space. Okay, so if you run this and you force it to segment that, to cluster that into two pieces, you get a segmentation that looks like this. Here I've told it to divide it into two. Okay, if you add if you add positional features, if you add x, y coordinate as another feature and tell it to divide it into two, you get something that looks almost identical to this. Okay, for a good time, you can add features. You can add positional features. You add x. So now the intensity, the features are x, y, and intensity, and tell it to divide it into three, and that's what you get. And the reason that I'm bringing this up is not so much to make fun of positional features. Well, not completely, but actually because this does demonstrate one of the things that's well known to go wrong with positional features, because it's sort of taking this background and kind of randomly dividing it into bits, because that's what position as a feature does. Okay, and that's what the result is of spatially coherent clustering, which I think is presumably what you want. Okay, now in fact the thing is that you really would like to be able to do your clustering in feature space with some knowledge of what's going on in image space as well. So let me show you another synthetic example. So here the left half of this image is a dark Gaussian. The right half is a mixture of medium and, that should be bright Gaussians. Let's cross that out here. So this is, so these two Gaussians are here. This Gaussian is there. Okay. Now, if you were to look at that and say, cluster that, give me a clustering, obviously you get that one. Suppose you were to look at that and say, well, give me a different clustering. What's your second best clustering? Your second best clustering is probably that one. Okay. So the point that I'm making here is that if you kind of, it could well be that the clustering you get gives you a terrible, gives you something that's spatially disastrous, but another clustering that wasn't quite so good would give you a really good one. So you want to be able to trade these off against each other, which I think is just a classic example of something you ought to be doing using energy minimization, to me. Okay, so let me just briefly introduce some notation. We've got a feature space. Feature vectors are, the feature vector for P is XP. For the pixel, we've also got a pixel labeling problem, and it's very important to remember that the labels we're going to associate with pixels are clusters, okay? Cluster 1, cluster 2, cluster 3. Furthermore, there's a set of cluster parameters, theta 1 through theta k, and you can just think of these as being the centers of the cluster, the Gaussian parameters, whatever. We're going to actually be able to handle non-parametric clusters as well, and obviously if there are no parameters, maybe you want to think of these as the histograms, or it's just something that gives the cluster's identity. The most important thing that you have to remember is that a labeling of the pixels gives a clustering in X. Okay, if I take my image and I say, these guys are cluster 1, these guys are cluster 1. Furthermore, these guys down here are cluster 2. Here's a big region which is cluster 2. Off in feature space, I've sort of said, here's where all the guys who are labeled 1 map to, they're that blob. Here's where the guys who are all labeled 2 map to, they're that blob. Okay? So pixel labelings give you clusterings. Okay. So what's the energy minimization approach? I think it's really obvious, and it's a very natural use of energy minimization. One of the great things about energy minimization, you know some things you want to be true about your solution, you just write them down. You want a spatially coherent pixel labeling, and you also want to penalize clusterings that are bad in cluster space. And here we're helped by the fact that there are a lot of clustering methods that themselves use energy minimization. Okay, there are many clustering algorithms that are based on energy minimization, or if you will, objective functions, which essentially where the way that they do clustering, let's forget about the image completely, just talk about a clustering problem in some feature space, is by minimizing or maximizing some objective function. And these include, for example, methods where each cluster is essentially parameterized by its center, and the clustering quality measure is the distances to the centers. Okay, so here's our energy function. Okay, it's defined on a labeling of pixels plus a set of cluster parameters. And basically what's going on here is that we have a term here that measures the quality of the clustering method, of the clustering defined by this labeling F, given the cluster parameters theta. Okay, so you've got this clustering, and so look, this labeling defines a clustering. Maybe the cluster parameters say that the center of this guy is over here, and the center of this guy is over here, in which case this is a really crummy clustering for these guys, but a pretty good clustering for these guys. Okay, and nice fact, this would presumably solve some of those examples I was showing you earlier. So lambda controls the relative importance of how important you think it is to be good in clustering space versus to be spatially coherent. Okay, so why not just do it? As I said, lots of experience with applying graph cuts. Again, there's a general problem here that I hope to interest you in. Just like in the mutual information case I showed you earlier, at the beginning of the day, we have absolutely no clue how much pixel P likes being in the ith cluster. We're not given assignment cost as input. Now, in fact, how much pixel P likes being in the ith cluster depends upon where the center of the ith cluster is. So for the pixel P, there's some point in feature space it corresponds to, so that's XP. And if the center of the cluster of the ith cluster is close to it, then it likes that label, and if it's far away, it doesn't like it. So it depends upon the cluster parameter theta I, which of course we don't know. But if we knew which pixels were in that cluster, if we knew that all these guys, that this was the clustering of things that are clustered over 2, from that we could compute the center of the cluster. So in other words, this is, I would claim, exactly the same problem. The data costs depend upon theta, in this case, which is unknown. But not only it's unknown, but it's computable from the correct F. So the obvious thing to do is you just iterate between them. So, yeah, question, Steve. Sure.
This issue of whether the spatial term is in the feature vector or not, it seems like it would give you could get an equivalent energy function. So, for instance, if you just have enlarge your feature vector, and you compute the norm between those two vectors, and you can separate that norm into 2 components, which is everything except the spatial terms, and then the spatial terms. So I'm just wondering how, that seems like it would be the same as the error term that you have there.
I've kind of thought about whether you could unify these things. It's tricky, and the thing is that the distance in along positional features is kind of this neighborhood distance, right? So you have a notion of, you want to be like your neighbors, quote unquote. But not, and so think about like the Potts model. It says it's good to be, that you want to be in the same cluster as your neighbors. But your neighbors, I mean, sure, you can sort of say it's sort of within a certain ball or something, but the Potts model really sort of says that there's a fixed cost there to be in different places. And it's sort of hard to sort of incorporate that into these clustering quality measures, because clustering quality measures are linear in a certain sense. So there may be some way of doing this in a, it would not surprise me if there's a much more clever way of kind of setting this problem up. I'm just, like I said, half-baked, right? Rick, did you?
I can think of a counterexample where I think a location-based technique, which is have no hook, and that's if you have the classic, double spiral with two things.
Yeah.
Black and
Yes.
white. Additionally, those things are distinguishable.
Yeah, I actually thought about using that as an example. Yeah.
We should talk after we get a chance.
Yeah.
All of these distance measures, just like you're saying here, the fact that you choose your distance measure can change during the algorithm as well.
Right.
And so, these spirals will work if you're allowed to change your distance measure, things like that. And
Yeah, and if you have models, right? If your clustering has complicated parameters, but then of course you can't actually compute them. Yeah.
There's a completely fundamental difference between making a distance in Latent space, which is an unknown parameter, and i.e. you want the two things to have the same label because they're near, versus saying that two things should have the same label because they have some other property. I mean, in hidden Markov models, this is extremely common, right? I mean, so you can have links. Right. I mean, if you want to draw a Bayes net, which is a hidden Markov model, you have links that can go up from the observations, and then you have links between the hidden variables. And that's what he's done, is he's added links between the hidden variables. I think everybody's comfortable with the fact that a hidden Markov model having constraints between the hidden variables is an interesting and different thing than some sort of observational penalty.
Yeah, but I still think, Paul, that there may be, maybe I'm wrong. I mean, this is at the end of my
presence of hidden Markov models would argue that you're wrong.
Yeah.
No, that you're right.
Yes. Oh, good. Well, in that case, I'll shut up and go on to the slide. Yeah. Okay. So in any case, so as I said, I mean, you probably at this point in this talk now seen kind of the punchline, right? These are the same problem, kind of. Okay. Same kind of techniques can be used for them. Okay. So here's our energy function. Here's our algorithm. Fix theta, compute d. Okay. We fix our cluster parameters, compute our data costs, and hence run graph cuts, get our labeling F, fix the labeling, compute theta.
This is a standard MRF. You're just learning the patterns of it.
Well,
or similar k-means. I mean, in this sort of definition, just a k-means problem.
Yeah. Well, this would be a k-means problem, except for the fact that we have a neighborhood relation where we're imposing spatial coherence on it, right? So I have gotten reactions, possibly even in reviews, that say that this is actually well known. However, I haven't actually found anything that really does this. Maybe I've just misunderstood them. Okay, and the thing is, so it is the case that there's a huge literature on clustering MRFs, et cetera, et cetera, et cetera. So I haven't seen things. There are clustering techniques. There are MRF techniques. I haven't seen ones that actually allow you to simultaneously say that you want things that are spatially coherent and also that good in cluster space, with the exception of there's a not very large body of work, which perhaps you guys are referring to, sometimes called segmentation-expectation or segmentation-maximization. There's a paper by American in PAMI fairly recently, and I have some references to it.
If you're doing the MRF with no observation model, you're doing inference on the MRF. If the observation model is not known, then you're learning the MRF. You're learning the parameters, not only on the distribution. You could even learn the parameters of your spatial coherence.
Yeah. I've never described
parameters of the model always.
Yeah. I mean, I tend not to describe stuff that I'm doing as learning for fear of being drawn into an area that I really don't know a whole lot about. As I said, I haven't seen work that actually allows you to trade. I mean, to me, what's distinguishing about this is the fact that you can sort of trade these properties. You have two different measures of goodness, and you can sort of trade them off against each other. Okay, but in terms of this, yeah, I mean, this is very much in the standard sort of parameter estimation clustering world. Okay, let me show you something that's extremely cute about this. Kind of a really nice coincidence. Maybe I'm being really lucky here. In order for this thing to work. Okay, where by work I mean, in order for you to be able to use graph cuts, you need Q to actually be in the correct form, which again is not so totally obvious. You need it to be the case that the quality of a labeling, given theta being fixed, is the summation. This is really not quite the right formula. The quality of f given theta, maybe, is of a form, a summation over pixels of the assignment cost. Okay. And I'm going to call that our linearity criterion. I'm open to better names for it, but that's I'll call it for the moment. It means that whatever your clustering method is, it has to have some kind of it has to be of this particular form. Linearity, fortunately, it turns out, is extremely common, and many of the popular clustering methods, including k-means and its very large group of cousins, meet the linearity criteria. So let's imagine that the cluster C sub k has a center little c sub k. I'm just doing k-means. Well, for these kinds of cluster methods, the quality of a clustering, given the parameters, is the sum over clusters of the sum over the things that are in that cluster of the distance between the thing in the cluster and the cluster center. Okay, and the only sort of free variable here is what exactly rho is. And if rho is the L2 distance, you get k-means. If rho is the L1 distance, you get k-medians, and there's just all kinds of related things. So it turns out, oddly enough, that we can actually, that our linear criteria is actually met by, just by sheer coincidence, by quite a large number of clustering methods. Okay, they actually are in the right form already. Okay, and that's because it's a relatively natural form. You know, how good is a clustering? It's a sum over how good, given a set of cluster centers, how good is a particular clustering? Well, if you score it, it's the sum over each element of its distance to the cluster center in some sense. Okay, you can actually even use this with non-parametric clustering methods, and this actually becomes very similar to what we did in the first part of this talk, all those hours ago, where basically if the histograms don't change very much between iterations, then non-parametric clustering can actually be put sort of in the same form as well. Okay, so that's it for the technical part of the last part of this talk. Let me just talk about experimental results. Yes, sure.
What I said earlier, so the novel, you do have novel thing here because you're using graph cuts for inference, which wasn't done in the context of learning in MRFs. Maybe that's what you should emphasize when you're listening to.
Yeah, I agree. I'm not claiming that this is it. Well, so the problem formulation as energy function that incorporates both spatial coherence and clustering goodness. You know, I'm not going to claim that that's a huge contribution, but it's pretty, and I haven't seen it. Okay, and maybe I haven't seen it because I didn't.
There's a higher level question.
Yeah.
Actually, I was talking to Chris Bregler about this, and he has the same higher level question. It seems when you're solving the MRFs with graph cuts, and when you're finding the exact solution in the first part of in the introduction of your talk, that also could be posed as a problem that has hidden variables, and people traditionally solve it with EN.
Yeah.
So, but you're able to solve it exactly.
The expansion of algorithm doesn't. Okay. Long answer. There are certain energy functions where graph cuts will find the global minimum. Okay. Those ones involve choices of V that are not useful in practice, in my view. So the algorithms that we're using, the expansion of algorithm is not guaranteed to find global minimum. Because, as I said, because that choice of V turns out to not be useful.
Two pieces of new research that we've shown here. There's no way of using graph cuts a little better, except in just the E step of the M algorithm. Somehow use it even, get a better solution.
That would be interesting. Yeah, I think it would be very interesting. I don't know. That would be. I think that as I said, I'd like to get you guys sort of excited about this project. There's a lot of expertise in this and related areas in this room. So maybe, hopefully, I've given you something to think about. Let me talk just briefly about experimental results. The results for this are extremely preliminary and annoyingly hard to evaluate for a variety of reasons. Feature space analysis is not generally a complete vision algorithm. It's used as part of something else. For example, it's used by Jitendra's group, and Jitendra, I think, does the best job of kind of explaining, all the steps of what he's doing. It's used by him to compute the affinities, basically how much each pixel likes another pixel, for graph-based segmentation. That's how he does texture. So he uses feature space clustering for textures without any spatial coherence, really. He just uses positional features, and then he runs normalized cuts. Okay, so that actually makes it very difficult to compare because the thing that I'm sort of advertising an alternative for, perhaps, is used as part of some other algorithm, and furthermore, that other algorithm is kind of tuned. Okay, it's got a lot of parameters, and they're sort of tweaked to sort of work well on their examples.
Can't you start with that solution and see if you can improve?
Yeah, that would be a good question. The experimental part of this work is not there yet. I'll show you a real data example in a moment. That would be an interesting thing to. But of course you can't. Right. But of course you can't tell whether you've improved it. That's the other thing. So there are good results on the synthetic data. I believe that I've discovered a new theorem that's very powerful. It's called the segmentation data theorem. It says for any segmentation algorithm, there exists some synthetic data that shows that the segmentation algorithm beats all others. I conjecture that this theorem can be generalized to other parts of computer vision. So we have our synthetic data. I think that, at least the synthetic data tries to show you something kind of interesting as to what's going on. But the experimental results are not there yet. Okay. I'll show you one example where you can kind of see something interesting going on. So here's this image. Here's a segmentation by mixture of Gaussians. And the only reason I'm showing you is that this is an example where you can kind of see that the segmentation, that the spatial coherence is buying you something, because there are all these holes here where mixture of Gaussians is using. And of course, someone who loves mixture of Gaussians would say, well, you just run morphological cleanup on this or something. I don't know. I think it's nicer to be able to sort of trade off these properties. But there are some other examples. The examples look reasonable to me, but I have just no understanding of what people in the world of segmentation are doing when they say that one algorithm is better than another. It reminds me of the bad old days of stereo. Okay, so let me summarize the second part of this method. I actually think that there's a fairly elegant way here of incorporating spatial smoothness into feature space analysis. I think it's very pretty. I would claim that this class of problems. Let's actually sort of think about this as if we were clustering people, which I'm definitely not. The problem of clustering, where you have a neighborhood system on the things that you're clustering, and you want things that are neighbors to be like each other, I think is actually an interesting problem, and one that has some applications beyond vision. There's some work in the clustering community on doing this kind of thing, but they don't really quite do. They tend to. They're not really. They don't have the same kind of constraints. It turns out actually that some of that work was done at Cornell, as I was shocked to discover the other day. Just down the hall. So it has possible applications beyond vision. The assignment costs, again, depend upon the labeling. And it's an EM style use of graph-cut algorithms. One of the biggest trade-offs about this work versus EM it involves hard versus soft assignments. Essentially, here's sort of a caricature of the trade-off. So soft assignments, where instead of a pixel being in a particular cluster, you think it's sort of 3/4 in this cluster, 1/4 in that cluster, have some significant advantages. In particular, in the M step, where you're sort of updating your estimate, they're actually they make certain situations a lot nicer. However, you can't really use graph cuts on soft assignments. So in exchange for having hard assignments instead, you gain the advantage that you can use a powerful optimization method, and that's, I think, a very interesting trade-off. Worth exploring. And it's also one of the most significant differences between what I'm talking about and a few other papers out there that try to do something somewhat similar. And then not much going on here in the way of guarantees. You have to experimentally, as always, the energy goes down. Okay, and you can just do the alpha expansion and check and make sure the energy is going down. But experimentally, it almost always does. Okay, so let me conclude. I hope to have convinced you that this class of problems, which involve pixel labeling with what you might call dynamic data terms that somehow depend upon the upon the labeling are actually important. They show up in a lot of interesting places. I think they're sort of mathematically interesting. Under some circumstances, you can solve them with graph cuts. The reason why this talk is not completely baked is that, while I hope I've shown you some interesting preliminary ideas, in terms of theoretical results and in terms of experimental results, we're really not quite yet where we'd like to be, and I'm hoping to persuade some of you in the room to help fix that problem. And I'm done.
We got some more questions. Chris, and then Paul.
So with the question, I've looked at some problems that are a little bit similar to this, and we can talk about top line brackets. One way you can get away from using the EM style and make that sort of more rigorous in terms of describing what the optimization procedure is by thinking it as a variational bound and thinking of it as using delta function approximations for these generation variables.
No, I got it.
Okay, so we have a way of formulating that, which I think we could really use.
That was great. Yeah.
Before I take Paul's question, let me just mention, anyone who'd like to talk with Robin, please come see me after the talk. Okay, there's already a few who lined up, but others want to add on to the schedule. So go ahead, Paul.
So just to try to follow the motion stop stuff, I mean, it seems like what you're doing here is taking something which is historically can be viewed as finding the maximum likelihood assignment of labels, and then you're wrapped into a model estimation aspect of this, right? So where the model could be a histogram, right? Where the model could be a mixture of Gaussians, or the model could be almost anything. So really, it's sort of like you're doing a kind of more classic joint model estimation and hidden variable estimation. Yeah. But by combining these things, which, a lot of terms which aren't quite those terms. Yeah. And so then the question is, formally, is there a big difference? Yeah. And, I'm going to bet Devotion's going to say no.
Well, the difference is using graph cuts for inference.
Right, so it's just a way of getting a maximum likelihood assignment.
A math assignment.
A math assignment.
Yeah. There's a French guy who calls this classification EM. His name's Bouvard.
Yeah, some people call it's the difference between hard clustering and soft clustering, and but the engine here is maybe the more difference, because everybody knows there's k-means and everybody knows there's mixtures of Gaussians, and that's not rocket science. I mean, and the k-means has problems.
Yeah. It would be nice to be able to say this problem, which I've been kind of waving my hands at, is the such and so problem. I just don't quite have one of those, a such and so problem. If we're going to sort of describe it as a particular problem, I would like at least to be able to sort of see clearly the some of these fundamental trade-offs in terms of, and especially with the clustering sort of energy function.
You said, for example, mutual information or joint entropy, it's kind of a funky measure. Yeah. But it is kind of like a log likelihood of the data. Yeah. Measured against the model which was estimated with that data. Yeah. Exactly. That's right. And that's a nice modulo some whole lot issues.
And that's right, Paul. And that's sort of a nice description because you've got the word data appearing. Yeah. I mean that sort of shows kind of the circular structure.
And if you're a little bit careful about how you're holding things out, you can actually just use that as a log likelihood.
Yeah. Well, as I said, it'd be among other things, it would be great to get people to explain to me what exactly problem I'm really. I mean, I don't claim to have invented this problem. It's a cool problem. Someone tell me what it's called. Because otherwise, let me put it this way: I would have had a much better talk title if I had known the name. Otherwise, I was going to call it "How to Use Graph Cuts to Solve Some Problems That I Don't Know the Name of," and Mike.
I think you mentioned at some point, I think your problem have things to set labels.
Yes.
Sorry. And you said you had some ideas about having k unknowns.
Yeah, there are some ways of sort of naturally defining energy functions that have, a little bit like MDL flavor. where, you count the number of labels and you sort of include that in the energy, and then you sort of consider splitting and merging. Vlad looked at that a little bit as we were sort of finishing up this paper. I don't think we have any great ideas, but those are sort of the flavor. There are obvious places where you can look at like splitting and merging kinds of things, and you can look, for instance, at splitting and merging where you use neighborhood information. Where you say, you want to merge this cluster, potentially merge these two clusters where they're actually, adjacent in the image. So that's the kind of thing. But we don't have any real good ideas about that yet. I just think that there are plausible ways of doing it. I don't see a plausible way of doing it sort of directly in the GraphCut sort of label assignment phase per se, although maybe.
Any other questions? Okay, thanks a lot.
Great, thanks. All right, so you guys are all going to